All right. Yeah.
All right, next speaker is Glaudell, who's going to tell us about unitary embeddings, linking gate teleportation to circuit synthesis.
Yeah, sorry, I forgot to say that I changed the title, but such is life. So I'm Andrew, and this is some work that I did with some of my friends, Matt Amy, Matthew Crawford, Melissa Macasieb, Samuel Mendelson, and Julien Ross. And this talk is going to be focused around the idea of catalysis in quantum circuits. So there is this very useful notion in the context of fault-tolerant quantum computing that gates can be implemented through resource states. And so the circuit I have pictured here is the gate teleportation circuit, where on the left side here, I have some resource state phi sub u, where this is basically dependent on some unitary u that I would like to implement. Now, in the context of fault-tolerant quantum computing, these things are often implemented through, say, a distillation protocol, for example. And then if I look on the other side of the circuit, you know, I can't just use that ancillary state. I also need to implement some unitary. But the kind of key insight in the context of fault-tolerant quantum computing is that this unitary that I need to actually apply can generally be easier to implement than u in practice. And so what we might see here when we look at this circuit is that the resource state phi of u gets eaten by running through this gate teleportation protocol. And so you might wonder, like, you know, does it have to be eaten? Like, what happens if that state doesn't get eaten? Like, can we still do anything interesting with it? And it turns out that we can. And I'm going to use an analogy from chemistry. So if there are any chemists in the room, please bear with me while I absolutely butcher your field. So in chemistry, we have this notion of chemical reactions, where we have some reactants made up of a number of atoms. And if the atoms are all the same on two sides of some chemical equation, they can in principle produce some products, right? But this doesn't always happen in practice, in reality. And oftentimes the timescales over which these reactions occur can be horrifically slow. So one very useful notion in the context of chemistry is the introduction of a catalyst. And so what a catalyst does is it basically lowers the activation barrier to being able to run through this chemical reaction, where my reactants can now interact with my catalyst, produce the products, and importantly, at the end of the day, in one hand, I can have my products, and in the other hand, I can have my catalyst back out, basically unchanged. And so we can kind of use this as a motivation for something we might want to do in quantum circuit synthesis, for example, where instead of reactants, I maybe have some target gates that I'm trying to compile into. And, you know, ideally, what I would like to do is find some exact circuit which implements some desired operation u. Now, in general, you're not able to do this. Like, you know, even though you have, say, like Clifford and T is a dense subset of like unitaries over complex numbers, you know, basically, if you pick a unitary at random, you will not be able to synthesize it exactly. But I'd like to, you know, suppose we use some extra catalyst state to try and allow this this operation to occur. And so what do I mean by that? I mean that we take some circuit C made up of, say, the target gates that we're trying to compile into, and try and act that circuit C on a product state, where it's basically a product state between some arbitrary state and this catalyst state. And then acting that circuit C on this product state yields for us basically the desired operation u. And importantly, when we look at sort of the action of C, the end result is this decomposed product state where we get back out our catalyst. And so if we think about something like catalysis in quantum circuits, really we're looking for something that acts roughly like this. And so, you know, does this actually happen in practice, right? Like, can you even do this? And the answer is yes. And it's actually, you know, a very familiar thing to, I think, a lot of people. And that is, so if you take a look at, say, like Magic State injection. So basically, this is the circuit you would run if you want to take a magic state and then use it to implement a T gate. Now, if you just take this circuit and replace the measurement and feed forward to implementing this S gate or not with just a controlled S operation, so basically I'm just like delaying the measurement in some sense, and I look on what comes out the other side without measuring, it turns out that actually on the other side comes out this magic state. And so when I look on the left side, I have some arbitrary state, my magic state. I look on the right side, I have some T gate applied to my arbitrary state and the magic state. And then curiously in the middle here, when I look at this, something very interesting happens. So this is a circuit. It's only got two elements, so it's not much of a circuit, but it's made up of Clifford and CS operations. Well, it's a well-known fact that T does not live in circuits over Clifford and CS. So what exactly is happening here? Well, it turns out that you can take CS gates and catalyze them into T gates using this reusable magic state. And so in some sense, T does live in Clifford CS, but it only lives in Clifford CS if I give myself access to one of these magic states. And the really crucial point here is this is reusable. Because I don't eat my magic state, I can actually use this to do any number of T gates. As long as I'm willing to always, apply a single CS gate, I will get out a T gate, right? So for a lot more analysis into things like this, I highly recommend the following paper by a couple heavy hitters. But I'd like to zoom in for just a moment on this bottom layer. So what exactly is this saying? It's saying that if the T states here, the magic states were replaced by, say, computational basis states. In some sense, it would be like saying that the circuit in the middle there is actually applying the T gate. But they're not computational basis states, they're this magic state. So in some sense, they're like a change of basis of the computational basis. And so really what this kind of construction is showing at some level, and please don't take this approximation sign too seriously here, but at some level, it's basically saying that the Clifford and CS circuits over Clifford and CS are exactly equivalent to circuits over Clifford and T, up to this change of basis. And that's kind of interesting because it's not at all obvious that this should be the case at all. And so that's sort of one interesting side of catalysis, but there's sort of the question of, are these things actually practically useful? And it turns out that yes, they are. So if I consider the synthesis problem, say, where I want to map some collection of gates to some other collection of gates, and I consider the cost in terms of, say, epsilon dependence, where epsilon is some precision parameter I want to hit. Roughly speaking, what this is going to cost you is every time you need to approximate a gate, you're going to eat something like a log 1 over epsilon raised to some power cost. Whereas if I do some exact replacement, if I actually have an exact circuit, it's something like order 1. I'm ignoring the size of the unitary effects here that come later if you really care about these things. But let's just think about this for a second. So if I were to synthesize directly, sort of, if you will, a standard approach, every approximation I do, so every gate that I need to approximate, I'm going to eat one of these log 1 over epsilon of the sequence, right? So I get something like a multiplicative scaling. But on the other hand, if I had some sort of catalytic embedding of each gate in the first set of gates to the second set of gates, then all I need to do is approximate the reusable catalyst. And because they're reusable, I only need to do it once, essentially. So I've basically taken something that's multiplicative scaling and turned it into additive scaling. So there's always exists some n in epsilon where this is an absolute win. So I'd like to think a little bit more about the structure of embeddings. And in particular, I'd like to focus on the problem of what happens when I try to embed in things like Clifford and T circuits. Well, and so just for going forward, I'm going to call this a catalytic embedding. Well, Clifford and T circuits have this really nice property that you can basically look at the matrices and decide whether it's a Clifford and T circuit right away, because basically you can look at the entries of the matrix in the computational basis. The thing here is called the numbering. It's not really important what this is. You can just think of it like a number system that includes one, addition, subtraction, and multiplication. But if I can basically find the numbering in which unitary descriptions of the gate set G lives in, then instead of having to worry about like things at like the gate or the circuit level, I can just talk about maps between collections of matrices, which is a little bit easier to sink your teeth into as someone who like comes from like an engineering background. Now, there's other things that we might want to build into Catalysis in general. So in particular, it'd certainly be great if all of the gates in a gate set G use the same catalyst, for example. We'd certainly like to be able to talk about matrices and not just circuits. We'd like the action on both circuits and matrices to basically be in harmony with one another. If there happens to be a particular gate which appears in, say, both the gate set G and Clifford, well, it would certainly be great if the embedding didn't touch that gate, just basically preserved it. And then finally, because we're going to be talking about maps between unitary matrices over rings, it will certainly be beneficial to try and take advantage of that ring structure. And so if we take all these things and stick them in a box and you can just give it a name and basically we'll call things with these properties linear catalytic embeddings. So you might ask, okay, you've introduced this thing that's, I haven't really defined it that much, but what exactly is a linear catalytic embedding and how do I build it in practice? And so I just want to consider one particular problem. So suppose I want to construct some linear catalytic embedding between basically, matrices over one ring, which is an extension of another ring, and I want to map into matrices over that smaller ring R. So what does this mean in practice? It basically means I can take a matrix M, which is one of these matrices that I'm trying to map out of, and I can write it as a sum of powers of alpha times coefficients, if you will, that are just matrices over the smaller ring. And so when I apply phi to n and just put in this replacement for n, and then I take all of those properties that I described on the last page. Unfortunately, I won't have time to go through it here. But the outcome is you can entirely describe the action of this linear catalytic embedding by simply describing the action of this linear catalytic embedding on this like one single number, this alpha here, that you are basically extending the ring by. Now, you might want to, we should probably consider like what are the properties of phi alpha. Again, I don't quite have enough time to go through all of those things, but ultimately, this problem of finding linear catalytic embeddings between this particular setup of rings and matrices boils down to finding some normal matrix whose entries belong to the ring R and whose minimal polynomial over R, basically the smallest degree polynomial over R that annihilates this matrix, is exactly identical to the minimal polynomial for alpha over R. And we call this a normal pseudo-companion matrix. And what's really nice is we don't have to worry about like, what is this catalyst state that I spoke of earlier? It's just the eigenvector of this particular matrix with the corresponding eigenvalue. So this boils down to the process of finding catalytic embeddings to something, tractable and like, basically takes a quantum computing problem and turns it into like a number theory problem at some point. So I'd just like to go through an example very quickly. So there are no third roots of unity in Clifford, but certainly what I can do is I can try and find a normal pseudo-companion matrix for a third root of unity with entries in the particular numbering corresponding to Clifford and T matrices. And so I can do that right here. Here's an example of one that satisfies those properties. And then I can find the eigenvector that corresponds to this e to the 2 pi I over 3 eigenvalue. And then if I take some matrix that has one of these third roots of unity appearing in it, I can just apply the same construction which I detailed on the last page, where I basically separate it out as a sum in terms of increasing powers of this third root of unity. I basically replace this third root of unity by this normal pseudo-companion matrix, and I put it back together. And then I can check, just as a sanity thing, like, is this doing what I need it to? And indeed, it is unitary. Indeed, when you act upon the catalyst, it gives you the action that you want. And what's rather cool is, sort of by accident, we've actually built a lot more into this than we necessarily had to. So if you can take the other eigenvector and consider the action in some sort of catalytic sense on the other eigenvector, with the same exact circuit, the same 4x4 matrix I have here, you actually get the dagger of the operation. And the reason is we basically built in automorphisms of the underlying number array into this construction, almost by accident, and which is rather cool. You can imagine that there might really be like algorithmic or some other kind of uses for this. If you want to talk to me about it, please do, because I'm not an algorithms guy per se. So just some other examples. So phase gradients have been known a lot about for a long time. Phase gradients are like literally just catalytic embeddings. Like, to a T, you look at what they're doing, you look at what linear catalytic embeddings are doing, and you're like, yep, those are the same thing. So in some sense, catalytic embeddings were born out of phase gradients. You can do totally wacko things. Like, you can find a normal pseudo-companion matrix for a 17th root, where you basically use this like famous construction of gaps to come up with this matrix. And in general, you can do any Fermat prime root of unity, find a normal pseudo-companion matrix. You can do square roots. You can just generate a good old random like normal matrix, and if the polynomial is irreducible, then you can implement that. So basically what I'm trying to get at is that Catalysis can inject all sorts of crazy gates into Clifford and T circuits with this nice scaling. Now, we studied this problem in detail over when you consider unitaries over fields and unitaries over rings. And so over fields, we basically closed the story in some sense. And the answer is basically you can always construct these things. And this construction is essentially optical. And I find the statement that you can do this always pretty interesting, because if we go back to that sort of like equivalence earlier, in some sense, it's just saying that unitaries over algebraic numbers up to some kind of change of basis are basically just unitaries over rational numbers, which I don't think would surprise mathematicians so much, but as someone who's like not like a born and bred mathematician, was like pretty interesting to me. Now for the ring case, which is unfortunately much more nuanced than the field case, but much more relevant, we haven't been able to completely close the story. Basically, we can't always find these normal pseudo-companion matrices, not that they don't exist. But we basically provide some partial results and some conjectures analogous with those for fields. And if you want to see these things, you'll have to keep an eye out on archive. The paper isn't quite out yet, but hopefully should be soon. Now, finally, I'd like to just briefly touch on, like, okay, so what is their connection to quantum? Well, we already talked about how they give this nice multiplicative to additive scaling, but they basically, if you go to Craig Gidney's blog and look up like how the heck do I implement the QFT in some smart way, the answer is like basically use like linear catalytic embeddings without then having that particular name, because Craig Gidney didn't name it. So in some sense, Craig Gidney was using these things and then using the fact that we have great synthesis algorithms over classical functions for his QFT description on his blog page. And then if we just take that contrived example I gave earlier, you can quickly do a back of the envelope and you find like you get like this massive T count reduction for like some reasonable parameter. So like these things are practically useful. Now, using this like phase gradient kind of construction, it's in some sense reproducing something that was known at least as recently as like a year or two ago. But it's basically this idea that Clifford plus diagonal Clifford hierarchy elements are in some sense just equivalent to like Toffoli and Hammond's. Like, and again, it's just up to this like little change of basis argument I made earlier. And then if you consider current conjectures or even some relaxation of these, it actually would imply that the Clifford hierarchy is basically just Toffoli and Adder. Like that's all there is to like qubit fault tolerant quantum computing, which I think is like a tantalizing little result. And I think it's something that people have like kind of been fishing around as an idea for a long time. So in conclusion, we've introduced this idea of catalytic embeddings. It's a whole bunch of things. It's a framework for circuit synthesis and circuit optimization. We gave some constructions and talked about unitaries over fields, but there are some open questions related to number rings, algorithms, and like connections to the Clifford hierarchy. So with that, I'd like to thank all of my wonderful friends here and tell you to please keep an eye out on archive for a series of upcoming papers on this stuff.
Can you comment on the number of TVs that you have to inject to, you said you can do this for the Fermat line. So can you comment on how many TVs you need to like inject this state?
Okay, yeah, so I should be a little careful here, right? So I have a number for how many T-gates you need to implement like a 17th root of unity as like a Clifford and T circuit, something that's isomorphic to it, and it's in the thousands, so it's like a lot. But that's completely unoptimized, and like that's basically me sitting down like rushedly before like the submission to QIP being like, maybe we should just do this to make it sound more exciting. So I would highly suspect that that can be optimized quite a bit.
Could you scroll back a little bit, like maybe the fifth slide?
Fifth slide.
Yeah, when you define the tensor of the catalyst state.
You mean that like maybe it's just like this thing?
Yeah. So in thermodynamics and entanglement catalysis, you can kind of strengthen your entire theory if you allow for a general correlated state, but the partial traces on the subspaces are exactly what we have. So C psi tensor catalyst would be some general rho, but on the individual subspaces you would have U psi catalyst.
Gotcha.
Is there a possibility to think about something like that?
Like so not just a circuit, but like just a general channel kind of or something like that? Or?
Yeah. So it basically weaken the condition, but as long as you kind of peel away in the catalyst state, you'll have the same state. So you might strengthen what you could possibly do.
Yeah, that certainly might be an interesting next place to take this kind of stuff. I think there's a lot of like little open questions here which would be interesting to tackle.
All right, let's